Hello, this video will cover exponential and logarithmic functions from the class NCBM 0114. This chapter, chapter 3 in the class Math 1314 Pre-Calculus is about exponential and logarithmic functions, and not only functions, but also equations and applications. And so we have to, first, we're going to go ahead and review the rules for exponents. And then from there, on the next video, we're going to kind of like translate those rules into the rules that we use for logarithmic expressions. There are a lot of similarities between those two sets of rules because we know at this point that an exponential function and a logarithmic function, they're inverses of each other. So first we have here the product rule. Whenever you are multiplying two letters, they are the same, you add the exponents. Then quotient rule, if you're dividing two letters, well, let me do an example with numbers. So for product rule, if we have something like x to the power 3 times x to the power 2, then we will be adding the exponents. So that will be x to the power 3 plus 2, so that will equal to x to the power 5. For the quotient rule, let's say that we have x to the power 5 divided by x to the power 3, and so what we do here is we subtract the exponents. So x to the power 5 minus 3, that will be x squared. Now, whenever we have the power of a number, which we call the power rule, we have to multiply the exponent. So assume that you have something like x to the power 2, and then we want to raise that to the power 3. So in this case, power of a power, we're going to multiply the exponent, so that will be x to the power 6. Now, if we have the power of a product, what we have here, the n is an exponent that is outside the product, x, y, and so what we need to do is distribute that exponent to both x and y like we have here. Now, we also have to distribute if we have an exponent affecting a ratio or a quotient like we have here, and that we call that power of a quotient. So we also go ahead and distribute x to the n divided by y to the n. Now, zero exponent, if you have anything except for the number 0 raised to the power 0, we will say that that is equal to 1. So we say anything, any number, any variable, any expression, except the number 0. 0 to the power 0 is undefined. But anything else to the power 0 is equal to 1. Now, the rule with negative exponents, whenever you have a negative 1, you assume you have a negative divided by 1 here. And so this rule tells me that if we switch the numerator and denominator, the exponent that used to be negative on top, now it becomes positive on the bottom. So those are the rules with exponents. Now, let's complete the blank here. So we have evaluate exponential functions, and we have this definition. So the exponential function f with base b is defined as f of x is equal to b to the power x, or instead of f of x, we could use the letter y to denote the output. Now, we call this exponential because the independent variable is the exponent, and b for base has to be a positive constant, but not equal to 1. It cannot equal to 1 because if that was the case, 1 to any power will always be 1, and therefore we will get a constant function instead of an exponential. So now, for example 1, we have to determine if those functions are in fact exponential functions. And so the very first one is not, because the independent variable is not the exponent, it's actually the base. And in fact, this is a quadratic function. It's also a polynomial function of second degree, or degree 2. Now the next one, it does work. The independent variable is right here, the exponent, and the base, which is the 3, is greater than 0, so that's okay. So this will be exponential for sure. Now the next example, we have the base is going to be 2, whatever is being raised to the exponent, and here we have x as part of our independent variable as part of the exponent, so yes, therefore it is an exponential function. Now, the next one, the problem that occurs here is that the base, for it to be an exponential function, the base must be greater than 0, and the base also cannot equal +1. However, here the base is -1, and so therefore it's not an exponential function because it does not satisfy the first requirement that says the base must be positive, greater than 0. So this is not exponential. So only B and C were exponential. For example 2, we need to evaluate the exponential function, and that function is 16 to the power x. We have it here. So here we're going to have f of 1 will equal to 16 to the power 1. So that is going to be equal to 16. For the next one, we have f of 1/2. And so that will be 16 to the power 1/2. Now here, whenever we have an exponent that is a fraction, that also represents a root. And in this case, because the denominator of the exponent is a 2, that denotes the index of the root, which is a 2. In other words, known as the square root. So the square root of 16 is 4. For the next one, we're going to have f of 3/2. And so again, we have an exponent that is a fraction. And so one thing we can do here to rewrite it, we could say 16 to the power 1/2. And then outside we will put a 3. So what we could do here is replace the 16 to the power 1/2 with the square root of 16. And then after we find that, then we raise that number to the third power. So square root of 16, we're going to use 4. And then 4 to the third power is going to be 4 times 4 times 4. And so that will be equal to 64. Now the next one is f of -1, and so f of -1 will be equal to 16 to the power -1. Now we're going to use that rule with negative exponents that says that we could always take the base 16 to the bottom, and now it will have a positive exponent of 1, and then here we need to have something on our numerator, so we put a number 1 right there. And that is the answer, 1/16. Now for the next one, f of 0, remember we're using this function, so it will be 16 to the power 0, and so that would just be equal to 1. Okay, so those are some values of an exponential function. Just as a quick recap, that the graph of an exponential function, for example, that one with a base of 16 will be an exponential growth function, and it does have that y-intercept at 0, 1, and then it also has this thing called a horizontal asymptote, which happens to be the x-axis. In other words, the equation y equals 0. That will be the horizontal asymptote. Now, for the domain and range of this function, of an exponential function, we could say that the domain is going to be all real numbers. In fact, your exponent could be positive, negative, 0. It could be a fraction. It could be a decimal. And our range is going to be any positive number from 0 to positive infinity. We use parentheses with 0 because 0 is not included. Now we're going to move on to how to convert from exponential form to logarithmic form and vice versa. So whatever we called the base of the exponential, right here, b, we use lowercase b to denote the base. We also call that the base for the logarithmic expression, and here it looks like a little subscript. Now, if you don't have a base, like is the case of this expression here, then we assume automatically that base is a 10. And base 10 is used so much that it has its own name, and it's called common logarithm. Now, if that base happens to be a number such as e, and just to remind you, e is approximately 2.71, although it's not recommended that you use 2.71 because you do have a button on your calculator if you have an 84, you should have a button on the left column that says ln, and then little it says like above the button, I would say e to the power x. So whenever you have that base e, also is used so much that it has its own abbreviation and its own name. It's called natural log, and we use the prefix ln or the abbreviation ln, which is natural log, which is nothing but a log base e. If you don't see the base, it's base 10. Now to convert from a logarithmic to an exponential, let's do some examples. So let's say that you have y equals the log of 5, and let's say the base is 2. So if I want to convert that to an exponential expression, I will always start with a base. Now in this case, it will be a big 2, and it will be raised to this exponent, and then whatever is left, such as a 5, that's what will go there. So now we could also convert in the other direction. So let's say we have 4 to certain power, let's call that a, and that will be equal to 16. So if I want to convert that to a logarithmic expression, it will be log, whatever is the base for my exponential, which is the 4, will also be the base for my logarithmic expression. And then we're going to have the 16 here. And so to answer this question, you could ask yourself, to what power do you have to raise 4 so that you get a 16? And the answer to that is 2. Also, if we were to say here 4 squared, that will give us 16. And so we are going to be doing this back and forth for the whole remaining of chapter 3 and pre-calculus. So now here we have a table of logarithmic equations and the equivalent exponential equation. Another rule that I really like to point out for that one will be this. If we have log with no base, we assume it's a base 10. Now, 10,000 is the same. Let's ask this question. To what power would you have to raise 10 to give you 10,000? The answer is 4, but let's see why. If you have a 10 and you raise it to the power 4, there is a rule, very nice rule, that states that anytime you're taking the log of a number, which is a big number, and your base is the same, then we can cross that out, and the answer is just whatever was remaining as the exponent. So to write this one in that way, it will be the log of 10. Remember, if we don't see a base, is a base 10. And so to answer this question, we do have an implied exponent of a 1 right here. And so we're taking the log of 10 with the same base 10. So that cancels out, and the answer is 1. Now, this rule is the same thing because we're stating log base e because we have ln, and we're taking the log of e. It doesn't have an exponent, so we assume it's a 1. And so the base and the argument, which is this big number, match. And so therefore, the answer is whatever is left there, which is that exponent of 1. And then finally here, this one, natural log. In fact, the log of any base of the number 1 will always be 0. Why? Well, if I rewrite this in exponential form, it will give me a to the power 0, and we know that is equal to 1, provided that a is not equal to 0. So now let's move on to our next page. And here what we're going to be doing is rewriting from exponential to logarithmic for example 3. And so we have on the first question, it says 2 to the power 3 is equal to 8. We know that it's true, so we're going to do, the first thing is write the word log. Then whatever is the base for our exponential will also be the base for our logarithmic. Now, this number here, 8, we're going to put it here. And then now we want to separate the 2 and the 3. So the only way to separate them is to send this little 3 over here to this other side. Next one is going to be log, then the base, which is 2. That will be our little subscript here. of 1 over 16, and the answer is -4. Next one, for this one, I'm going to rewrite it this way. So this is the same as 8. Remember what we discussed about exponents that are fractions? So we have a cubic root. So that will be 8 to the power 1/3, and that will equal to 2. So now to write that as a logarithmic expression, it will be log. The base here is the big number here, 8. So now the base of a logarithmic will be the little number. And then now we want this 2 to be with the log, and then we want this exponent to be over here. And that is the answer. Now for the final one that we have here will be log base b of 1,000 is equal to 3. Okay, now we're going to do the opposite. So we're going to rewrite the logarithmic expression into an exponential one. And so here, same thing. The base of the logarithmic is also the base of the exponential. So it's going to be 2 to the power 6, and that is equal to 64. So if you notice, I'm separating the 2 and the 64. Here, I'm going to start again with the base. So 6 to the power -2 is equal to 1 over 36. And the last one will be 49, which is the base to the power 1/2, and that is equal to 7. Just to write it another way, the square root of 49 is 7, so it does work. And here, this one, remember, if you have a negative exponent, we could bring that 6 to the bottom. It will become positive, and then the 1 on the numerator. And so you could see how 1 over 6 squared is the same as 1 over 36. And here, if we multiply 2 times 2 times 2 times 2 times 2 times 2, we will get 64. Now let's do the ones here on the bottom, and here we'll have b to the power 3 is equal to 27. The next one, remember, natural log, or ln, is a base e. So here we have e to the power 1.9459 is equal to 7. And that's it. Now, the last concept that we're going to address here on this handout will be the change of base property. And we do go over this because calculators, most of them, they only have 2 types of logs that you could find. And that will be common log, which we already discussed is log base 10. And then ln will be the log base e. And that's why you have this second functions by those buttons. So now some calculators can calculate any type of base, but back in the day it was just that. So the idea is that we're going to use either base 10 or base e to be able to solve those logarithmic expressions. So here we have the log of x base a. And so if you want to convert that into a base, any base, of course, you will take the log of the argument, when in this case is x, and then divide it by the log of the base. So if we do that with base 10, it will be log of x divided by log of a. Now, it's important to notice that we are writing, and therefore we will type that in the calculator twice, the log or the ln key. Since we are taking ratios, we could also achieve the same result, changing the base to base e. So natural log of what is your big number here, and then divided by the natural log of a, which is your little number here. So let's go ahead and apply that, the change of base formula. So in this case, we could calculate the log of 2,506 divided by the log of 7. Now, that answer will be an approximation, of course, and that will give us the same as if we were looking for this, the natural log of 2,506 divided by the natural log of 7. So number 2, we could also do the same. We could take the log of 13. Remember, if we don't see a number as a base 10, divided by the log of 5. We could also get that if we take the natural log of 13 and then we divide by the natural log of 5. And then finally, for number 3, we will be finding the log base 10 of 63 and divided by the log of pi, also base 10. That will give us an approximation. And here for this one, it will be the natural log of 63 divided by the natural log of pi. So when you enter this on your calculator, for example, this one, you have to make sure to press the key ln twice. So it will be the natural log of 13, close your parentheses, then division symbol, and then you have to enter ln again. And then your number, and then finally, you will press enter. Now, one important thing to mention is that this expression does not equal, and you have to be very careful, it does not equal the natural log of 13 over 5. That expression is completely different. This is the natural log of the fraction 13 over 5, and this is the ratio of two natural log expressions. So in the meantime, try to find those with your calculator. And I'm going to be writing that number myself as well. Like I was saying, it's very important to enter natural log twice. So for the first one, I got 4.022. And if I was to calculate it with common log or log base 10, I will get the exact same thing. Now for the next one that we have the natural log of 13. And is divided by the natural log of 5. And for that one, we're going to get 1.594 if we were to round to the nearest thousand. So one more left to do, and that will be the natural log of 63 divided by the natural log of pi. And so I will recommend that you use the button for pi so that you get a better approximation, especially for my MATLAB purposes. And I get here 3.619. If I was to do that with common log, we should be getting the exact same thing. And so we have it right there. And this concludes the end of the video, so thank you